So now that we have seen how the transpose of a matrix can be useful, we're going to record some important properties. First, if A plus B is defined, then the transpose of A plus B is a transpose of A plus the transpose of B. If S is a scalar, then SA transpose is S times A transpose. The transpose of the transpose is simply A. If the product AB is defined, then the transpose of AB is B transpose times A transpose. Note here that the order of multiplication gets switched when you distribute the transpose. For a square matrix C, the inverse of the transpose of C is the transpose of the inverse. And finally, the transpose and the original matrix A both have the same rank. So an important consequence of the last property of the transpose is that if V is an n-dimensional subspace of Rm, then M is equal to the dimension of V plus the dimension of its orthogonal complement. To see why this is true, first write down a basis for V. Since V is an n-dimensional subspace of Rm, there exist n linearly independent vectors so that V is equal to the span of the vectors v1, v2, down to vn. We can use these basis vectors to create an m by n matrix A with columns v1, v2, down to vn. This allows us to view V as the column space of the matrix A. So we can think about the orthogonal complement of V as the orthogonal complement of the column space of A. And as we saw last time, the orthogonal complement of the column space of A is the null space of the transpose of A. Next, we use the rank nullity theorem. The dimension of V plus the dimension of the orthogonal complement can be expressed as the rank of A plus the dimension of the null space of A transpose. We use the fact that the rank of A and the rank of A transpose are the same, and this is where the rank nullity theorem comes in. When we add those two together, we will get M. And this is because A transpose can be thought of as a matrix transformation that goes from Rm to Rn because it is an n by m matrix. So to see how this is useful in practice, let's suppose that we're given a plane in R4. And this plane is defined by the vectors u with entries 1, 0, 2, -1, and v with entries -1, 2, -6, and 3. Because this plane lives in R4, its orthogonal complement will have dimension 4 minus 2 is 2. So if we wanted to find the plane perpendicular to V, then we can do this by first computing the transpose of the matrix with columns U and V, and then computing its reduced row echelon form. So to find exactly which plane V perp is, we just need to observe that it is cut out by the two equations x1 plus 0x2 plus 2x3 minus x4 is equal to 0, and 0x1 plus x2 minus 2x3 plus x4 is equal to 0. So we can see here that V perp will indeed be a plane, since it is a two-dimensional subspace of R4. Explicitly, we can see that V perp which is the null space of this transposed matrix, is the set of four-dimensional vectors with coordinates x1, x2, x3, and x4, subject to the constraint that x1 plus 2x3 minus x4 is 0, and x2 minus 2x3 plus x4 is equal to 0, which of course we can rewrite as the two conditions. X1 is equal to negative 2x3 plus x4, and x2 is equal to 2x3 minus x4, which we can also represent as the set of vectors negative 2x3 plus x4, 2x3 minus x4, x3, and x4 parametrized by all pairs in R2, x3, and x4. And of course, we can split these as two vectors, x3 times negative 2, 2, 1, 0, plus x4 times 1, 1, 0, 1. So this is the span of those two vectors, negative 2, 2, 1, 0, and 1, 1, 0, 1. So this tells us how to find the orthogonal complement of a given subspace of Rm, and also how to find a basis for such a space. And that is it for our discussion on the transpose and orthogonality.